Okay, get ready for this. Imagine holding a star in a jar, a tiny little point of light that gets hotter than the surface of the sun. But it's not made from nuclear fusion. It's made from sound. Yeah, sound. It sounds completely impossible, but this is a very real and very bizarre phenomenon, and we're going to break down exactly how it works.
So, the big question is, can you really do that? Can you actually take a sound wave and turn it into a flash of light? Well, the answer is a huge yes, and it turns out the process is one of the most extreme events we can possibly create in a laboratory.
The official name for this incredible process is sonoluminescence. And here's the gist. You take a sound wave, you trap a tiny gas bubble in some liquid, and then you use that sound to squeeze the bubble so hard and so fast that it just implodes. And in that moment of collapse, it lets out this stunning burst of energy as light.
So, how on earth does this actually happen? I mean, the science behind it is just as wild as the idea itself, and it all begins with a very specific, very precise setup. Okay, so this is what it looks like. You start with a flask of water, nothing too fancy, but it's often seeded with a noble gas like argon or xenon. That'll be important later. Then you have what's called an acoustic transducer. You can basically just think of it as a really powerful speaker that blasts the water with a strong standing sound wave. Now this graph is really the key to the whole thing. The blue wave up top, that's the acoustic pressure from the transducer. When the pressure goes down, the bubble, shown by the orange line, slowly and gently expands. But then when that wave crests and the pressure just skyrockets, bam! The bubble is crushed with unbelievable violence. And this cycle happens over and over, thousands of times a second.
So it really all boils down to this insane, repeating four-step cycle. First, a tiny bubble gets trapped in the sound wave. Then, that pressure wave collapses it with just astonishing speed. Right at the instant it hits its smallest possible size, it flashes with light. And then it just rebounds and settles, ready for the whole cycle to start all over again.
So in theory, it's this really beautiful, elegant cycle, right? But in the real world, trying to actually study this tiny, violent event was a huge challenge for scientists. At first, all they had to work with was just a chaotic mess.
You see, the early experiments created what's called multi-bubble sonoluminescence, or MBSL for short. And it looked like this, a chaotic cloud of countless little bubbles all collapsing, all interacting with each other. And you can see the problem right away. How could you possibly study the physics of one bubble when it's being slammed around by thousands of its neighbors? It was almost impossible.
But then, the game completely changed in the 1990s when scientists figured out single-bubble sonoluminescence, or SBSL. And as you can see here, by isolating just one stable, oscillating bubble, they finally went from that chaotic mess on the left to this perfectly controlled environment on the right. This was huge. It gave them clean data, a brighter light, and it meant the real mystery could finally be investigated.
And this quote really gets right to the heart of it. Even when you have just one bubble, how do you measure what's happening inside something so small that collapses so mind-bogglingly fast? It's like trying to take the temperature of a lightning strike.
This challenge, figuring out how to peer inside a single, tiny bubble, is what finally let the real investigation begin. Moving from studying many bubbles to just one set the stage for this amazing scientific whodunit. What exactly was happening inside that bubble to create the light?
As it turns out, two main suspects emerged. On one side, you had theories that said it was all about electrical processes, basically a tiny little spark. And on the other side, you had theories that argued for thermal processes, the creation of an insanely hot spot.
So, the case for an electrical cause went something like this. As the bubble collapses, positive and negative charges get separated on opposite sides. The voltage would build and build until, zap, you get an electrical breakdown, a spark, that creates the flash of light. But, and this is a big but, this idea really only works if the bubble collapses unevenly.
Now for the other suspect. This one is known as the hot spot theory. The idea here is that the collapse is just so fast, we're talking microseconds, that there's absolutely no time for heat to escape. All of that energy from the collapse gets converted into immense heat and pressure. The gas inside gets so hot that it actually turns into a plasma and starts to glow, just like a tiny piece of a star.
All right, so we have our two competing theories, a tiny spark or an incredibly hot spot. So let's look at the evidence and see which one of these theories actually holds up.
Okay, this right here is a critical piece of the puzzle. This table shows how bright the light is when you use different noble gases. And as you can see, xenon produces a much brighter flash than helium. This find strongly supports the thermal hotspot theory. And why is that? Well, because heavier gases like xenon are worse at conducting heat. They trap it more effectively. They're also harder to compress, which means they get way hotter during the collapse. And that leads to a much brighter glow.
And this image does a great job of showing what that leading theory looks like in action. The hotspot model shows that right at the moment of collapse, this unbelievably hot core is formed, with all the energy focused right into one microscopic point.
So, exactly how hot are we talking about here? Well, some theories and measurements suggest that the peak temperature inside that tiny collapsing bubble can reach as high as 20,000 Kelvin.
Let me just say that again so it sinks in. For a fraction of a second, in a tiny bubble, in a simple flask of water, you can create conditions that are potentially hotter than the surface of our sun, and you do it all with the power of sound.
Hotter than the sun. It's just an absolutely mind-bending result, isn't it? A conclusion that seems like it should break the laws of physics, yet it's backed up by some pretty strong experimental evidence.
And, while the hotspot theory is definitely the leading explanation right now, the science here is far from settled. This phenomenon is just so extreme that it pushes the very boundaries of our understanding of physics, and it leaves us wondering, what other secrets are still hiding inside this tiny, violent star in a jar?